A significant real-life application of intermolecular forces is chromatography. But what is chromatography? Chromatography is used to separate mixtures of pure substances into their components. Imagine that you have a room full of an unknown mixture and you want to find out what it's made of. How would you do that? Well, first you add the substance to what's called a mobile phase or a group of pushers. These pushers will then push the components of the substance across the room. However, some of these substances will have more corners, which represent the strength of the intermolecular forces. Naturally, these corners might get caught on a bump in the carpet. Other substances, however, will be easier to push, meaning they have weaker intermolecular forces. The substances that are easier to push will therefore reach the finish line faster compared to the other substances. By measuring how fast a substance reaches the end, or how far the substance reaches, you will be able to identify what this mixture consists of. And that is chromatography.
All right, let's begin discussing a little bit about how chromatographic separation works. I want to give you a quick rundown and an animation of some of the underlying principles and sort of how to think about the way a molecule will behave in one of these chromatographic systems. We're going to start with a question. How does partitioning between stationary and mobile phases help us separate the components of a mixture? So we're going to get down to the underlying root principles of chromatography here. First, we're going to go through our cast of characters as we normally do. We'll be using gray spheres to represent the silica surface of a normal phase TLC plate. Now, this could just as easily be alumina or some other relatively high polarity material, but silica and alumina are the two that you'll see the most of. Next, we'll be using blue spheres to represent the solvent molecules as they move through the system. These would be the mobile phase. We'll be using a yellow polygon to represent low polarity compounds, and a purple polygon to represent a higher polarity compound within the mixture, so we can see how the polarity of different compounds will affect their behavior in a normal phase chromatographic system. So let's begin, as we normally do, by looking at the system we'll be using, but zooming in so that we're looking at it from a molecular perspective. If we zoom all the way in to the base of the plate at the molecular level, what we'll see is a stationary array of silica beads over which is flowing a moving array of solvent molecules. These are the stationary and mobile phases. Now, if we introduce one of our compounds to the system at the upstream end, in this case the higher polarity compound, we can watch and view what happens when I release this compound and allow it to do what it does when it's in this chromatographic system. So let's do that now. Notice that when I release this compound, it's swept along by the mobile phase, but it occasionally takes a break and adheres to the silica surface on the stationary phase. Because of its high polarity, it spends a large portion of its lifetime adhered to that surface, and therefore it moves very slowly from one side to the other. Now, in contrast, let's take a look at the lower polarity of the two compounds. If I similarly introduce this compound into the system at the upstream end and then release it, let's watch what happens. Again, it moves when it's in the mobile phase and is stationary while on the silica, but notice that the residence time on the silica is very low now because its relative affinity is decreased compared to the higher polarity material. What this means is that the compound will move faster through my chromatographic system. Now finally, to illustrate how we can separate compounds using this phenomenon, let's put both of those compounds into the system simultaneously. When I release them once more, let's watch what happens. Again, they're swept along by the mobile phase, but our yellow compound is moving at a higher rate of speed because it spends more of its lifetime dissolved in the mobile phase and less of its lifetime adhered to the stationary phase. In this way, we can separate two different types of compounds in space, even though they were part of the same original physical mixture. Now let's take a look at how a TLC plate will behave on the macro scale. So this time we'll zoom in, but not quite as far. This time we'll be using the entire surface of the screen to represent the surface of a TLC plate. To begin the experiment, we need to draw a starting lane so that we have an idea of where exactly our compounds were when the chromatographic separation began. At this point, we're going to spot our compounds or mixtures of compounds onto the plate. For demonstration purposes, I've created spots of pure purple compound and pure yellow compound. Now that the spots are in place on the starting lane and appropriately spaced, I'll introduce the mobile phase to the system and allow it to wick up from the bottom to the top of the plate, carrying along my analytes at whatever speed they may go depending on their partitioning behavior. Here comes the mobile phase. And as you can see, again, our yellow compound, by virtue of its lower polarity, moves a greater proportion of the distance traveled by the solvent or by the mobile phase. We can qualitatively at this point say that our yellow compound moves farther than our purple compound in this system, but we prefer to have a quantitative method of describing this behavior. To do this, we measure the distance traveled by the solvent. We also measure the distance traveled by each spot from the starting lane to the center of that spot. And we then calculate a number called the retention factor, which is equal to the distance traveled by the sample divided by the distance traveled by the solvent. In this way, we have a numerical value to associate with the mobility of each compound. The RF of our yellow material would be larger than that of our purple material, indicating that it's expected to move at a higher rate and therefore a greater distance, and therefore must be a lower polarity material than the purple compound.
In this lesson, we will learn about paper and thin layer chromatography, both of which are used in forensic science applications. Chromatography is a separation technique, and this will be demonstrated using food coloring. Using a pencil, draw a line at the bottom of a strip of chromatography paper. Dab a small spot of red food coloring on the pencil line and repeat with green and blue food coloring. Place this in a beaker with water, ensuring that the water level does not touch the spots. As the water is absorbed, it separates the multiple components of the food coloring. We have now created a chromatogram. The chromatography paper is called the stationary phase as it stays put. Water is called the mobile phase as it moves up the chromatography paper. Here is the key idea. A component that is more soluble in water travels a greater distance up the chromatography paper, and a less soluble component travels a shorter distance. The retention factor, or RF value, is a measure of the distance that a separated component has traveled compared to the distance that the solvent, in our example, water, has traveled. These distances can be measured using a ruler. What does the retention factor value tell you about the solubility of a separated component in the mobile phase solvent? Please pause the video to think about this and resume when you are done. A larger retention factor value means that the component is more soluble in the solvent. A smaller retention factor value means that the component is less soluble in the solvent. Thin layer chromatography, or TLC, works in exactly the same manner. Instead of chromatography paper, a glass plate with a thin layer of silica gel or any other adsorbent material is used. This thin layer of adsorbent material is the stationary phase. A suitable solvent may be used as the mobile phase. If the separated components are colorless, the dried chromatogram may be sprayed with ninhydrin, which can turn some components purple, or the chromatogram may be viewed under UV light. Ninhydrin is used to detect fingerprints from a crime scene. These chromatography methods can be used to identify and compare samples of drugs, inks, lipsticks, saliva, and explosives, just to name a few. In conclusion, paper and thin layer chromatography are used to separate components of a mixture based on their solubility. The relative solubility of the separated components can be determined by calculating their retention factor values. More soluble components have a larger retention factor value, and less soluble components have a smaller retention factor value.
A water softener is by far the most efficient way to remove hardness from water. Softeners have two main components, a brine tank that holds the salt and a resin tank that holds the resin. All-in-one water softeners have a resin tank located inside the brine tank. Water softener resin inside the resin tank consists of very small granules slightly larger than grains of sand. Here we show an enlarged representation of resin beads inside a water softener. As well water flows through the resin bed, the negatively charged hardness molecules are magnetically attracted to bond to the positively charged resin. This process removes the hardness from the well water, creating softened water. Once the softener's resin is full of hardness, it has to be cleaned using a process called regeneration. When regeneration begins, a valve shuts off the flow of water to the house and begins to draw salt brine water in from the brine tank. This brine water is then circulated in the opposite direction of the normal flow of the water, removing the hardness from the resin. The brine water is then drained from the resin tank, the resin is thoroughly rinsed, and soft water production begins again.